And
Hello and
we are live.
welcome. Hello and welcome to the Digital Futures session on 3D printed bridges. A session that I think will, a session I think which will be one of our most significant ones in that it is very precisely charting a history of a certain form of construction in which Digital Futures itself has been, through Philip Yuan, has been very heavily involved. Let me start though by, before I introduce our speakers today, just say that we are an interesting moment actually. Yesterday we held our first ever Spanish language session, and it was a huge success. This builds upon our other language sessions, our Arabic and Farsi sessions that we've done, in addition to our Chinese language ones and of course our English language ones. We shortly hope to have some Portuguese sessions starting. And then tomorrow we have a session as part of our doctoral consortium where Blaise Agiriakos will be coming. This is a theoretical a series of debates for doctoral students worldwide. And we're bringing together some of the leading thinkers from the world of neuroscience and AI and architecture to talk about the emerging theory of intelligence, something that's very central to all that we've been doing. Philip Yuan has just launched a journal called Architecture Intelligence, and the theme of intelligence runs throughout all the conferences that we've been organizing in recent years. So there'll be a kind of Spanish flavor in many ways to tomorrow, because Blaise comes from Barcelona, and indeed today we have some we have a IAAC from Barcelona being represented. That'll be tomorrow at 1 hour later than today's, and we're part of a series. And we are we're delighted to have some very significant people added to the list of speakers for this and guests for this particular series, including Antonio Damasio, one of the world's leading neuroscientists, and Andy Clark, who was one of our guests, sorry, at Digital Futures as our keynote speaker a few years ago. So today, in many ways, a very historic session, because we are. It is, I think, the first time this has been addressed in any way. It's also the first time that we're looking at the first ever 3D bridges, at least what we think are the first ever 3D bridges. Let me say first of all that Areti Markopoulou has had to pull out, unfortunately, the last moment because of a family emergency. But I'm delighted that in her place we have Rodrigo Aguirre, who has been the computational expert between the bridge that was designed by IAAC. I'm also absolutely delighted to have Enrico Dini here. Enrico is one of the pioneers of the world of 3D printing, a hugely significant figure, and he was involved in the bridge for IAAC. I will say something by way of introduction to Enrico's work after this. Of course, it's always a delight to have Philip Yuan here. Philip was the co-founder of what became known as Digital Futures back in 2011, and has rose in prominence both as an architect, as an academic. He's the vice dean of Tongji University at the moment, and has been a pioneer in 3D printing itself. Finally, it's always a delight also to welcome Shajay Bhooshan. Shajay is someone that I've known from years ago. I can recall inviting him to the University of Brighton back in 2008 to give a lecture, but even before that, he was part of the ZHA DRL scene. And Shajay and indeed Patrick have been fundamental to the whole Digital Futures project in supporting us over the years. Shajay was, of course, in one of our best ever sessions on the ZHA code that immediately racked up several thousand views. So today we're going to talk about three bridges. This one I won't say much about. You can see Enrico in the middle here. It's a building that was put together by IAAC, and Enrico was involved at the very beginning of the process, and we'll hear the story from Enrico, and then Roberto will tell us more about the bridge itself and how that was designed. We can also see Areti on that bridge there. Unfortunately, isn't here. And then we're going to look at this bridge, the bridge by one of many, shall we say, by Philip Yuan. Over the years, he's been doing two bridges, in fact, every single year as part of the Digital Futures project in Tongji. I think it's 5 years. Anyway, I'm looking forward very much to seeing the overview of those projects. And we'll finish up with this remarkable bridge that was completed this year. So it's a very recent one, which is a collaboration between Philippe Bloch's research group and ZHA Architects. And Shajay Bhooshan will be talking about this particular bridge. But just to set the scene for all these 3D printed bridges, I want to just go back in history. It's not often that when you've got the name Futures in the title of an organization, you look back. But I think it's worthwhile just looking back to see how new this world is and where it emerged. Back in 2009, there was an exhibition in Barcelona that was organized, curated by Marta Malay, and it was really charting the state-of-the-art 3D printing that was going on in the world at the time. A really remarkable exhibition. And this is the Gaudi chair, one of the exhibits there. And you could see already that there was something emerging back in 2009 that was highly significant. Items in the house itself, tables, chairs, and so on. Clearly, that something new had arrived on the scene, and very significantly too. And it wasn't just these furnitures; it was also these outfits. This kind of chainmail logic had been used to explore how you could produce clothing. And of course, a few years after that, Ben Asfarai and I edited an issue of architectural design on 3D printed body architecture, looking at this. A number of architects who were involved in this kind of world. There were shoes and even prostheses. It was a very interesting exhibition, but the architectural side of things was actually relatively behind. While all the items in the house had been 3D printed, the house itself was very far from being 3D printed. So these were the three exhibits that Marta put together for this exhibition. In the background, a chaise longue that was designed by Colmac and fabricated by Enrico Dini, really a pioneering effort. In the foreground, some small samples from Baroque Hoshneves, who was probably alongside Enrico, the leading pioneer at the time. And in the middle, there's a piece that was done by a group at Loughborough University in England that was initiated by Rupert Saw. But this was it. This was it. Compared to the rest of the exhibition, which was very, very advanced, architecture and the world of 3D printing buildings was relatively far behind. I'm delighted that you have Enrico here today. He was absolutely a pioneer in this. He established D-Shape many years ago and was really very significant. So I'm not going to say much about it. It's simply to point out that his early pioneering work with D-Shape, where he was effectively 3D printing using a giant Z-core printer with his own proprietary method, was really a great breakthrough for the world of 3D printing. And these were the components that he assembled into arguably was probably the first ever building as such. I mean, how do you define a building? But this was an enclosure, and Enrico was responsible for this, alongside the chaise longue that Sulaim Colotan and McDonald they designed in New York, and it was fabricated in Italy. The other great significant figure at the time was Baroque Hoshneves, who was an Iranian-American engineer based at the University of Southern California, with whom I collaborated when I was at the University of Southern California. And let's not forget that Digital Futures itself was a collaboration initially between USC and Tongji in Shanghai. And Baroque himself came to one of our events to talk about his work. And this is contour crafting. This is the technique that Baroque established, a very different technique of layered concrete construction, where the concrete was extruded like toothpaste, and there's a spatula that was smoothing out the edge, so we get a much smoother finish to that. And this was very, very carefully controlled by Baroque. He built a few example walls, but didn't necessarily go so far as to build a building as such. When Baroque came to Shanghai for the Digital Futures event, we introduced him to one of the local fabricators with the idea of some kind of collaboration. In fact, there wasn't much collaboration, but Winson of Shanghai did build what they claimed to be a series of the first 3D printed buildings. I would claim that Enrico's was already there, but there we go. And what was interesting is they effectively borrowed the technique from Baroque. Baroque was actually quite flattered by this, and he was interested to find out that, in fact, the technique that he'd imagined would work of internal reinforcement actually did work. Anyway, these buildings were built, they claim to have been built in 24 hours. Baroque is somewhat suspicious of that. He thinks that it would have taken much longer for the concrete to cure in the factory before putting them on site. But it was done in the factory and then assembled on site. Since then, they've gone on to produce things like this, and one could say that the whole field of 3D printing has really evolved. These are early examples of buildings in UAE, United Arab Emirates, where you can see that 3D printing has come of age, and it would be impossible to do a survey of what's been happening recently because the whole field has exploded. And with the use of robotic arms and different materials for printing, the possibilities have really enlarged. We've moved beyond the bed of the 3D printer to something which is so much different. But I want to briefly also mention another aspect of this rivalry. I say a friendly rivalry because I actually introduced Enrico and Baroque at the Bauhaus, I think in 2013 or something like that, 2010 or 11. And they got on very well. And this was we had a conference there about extraterrestrial architecture. And this was, there were two different ventures going on at exactly the same time, intriguing in many ways. One was a venture that was sponsored by NASA. This was the one in which I was involved with Beroko Nevis, with Anders Carlson and Matu Thangavello. This is our contour crafting machine on an athlete hopper, printing material on the moon out of regolith. So to house landers, it wasn't to make habitable dwellings, different, unlike the European Space Agency, who would fabricate complete buildings. NASA's project was to send the building already assembled to the moon. And then alongside this was a consortium in which Enrico Dini was involved, that involved Norman Foster Associates and several other organizations, which was looking at how you might actually fabricate a building on the moon, a complete building. This was sponsored by the European Space Agency, and we were unaware of each other. I think the fact that these two competing consortia were developing this, but this was a very different sort of way, where these mini little robots were printing onto a kind of inflated formwork and producing something remarkable. So that was back 2012, 2013 when these things were happening. And since then, of course, 3D printing has exploded. It's become a major event. And we want to kick off today's session by looking at this bridge, and particularly the background behind this bridge. The first bridge that we think, anyway, was 3D printed. And I'd like to welcome Enrico Dini. It's such an honor to have Enrico here today, as such a pioneer of the field. We don't have to go back that long. It's a new field, but Enrico was one of the leading things and still remains that. So I would like to welcome Enrico and invite him to share his screen and to tell us something about the background behind this historic bridge. Enrico, welcome.
Thank you, Neil. I'm overwhelmed and honored to be here today. And in honor of you, Neil, I prepared the first slide to celebrate the meeting with Beroko Koshnevitz. I was really amazed by the first slide that you share in your presentation, where I was reputed as Mr. Henry, I don't remember how, who met Mr. Livingstone. And to be honest, Berok and I were quite suspicious each other because we never met before, but rapidly we became a friend. And we independently and without awareness of each other, we developed our own systems, and I discovered about Berok works. Over a year later, I started my way to interpret additive manufacturing applied to architecture. So, Dr. Koshnevitz, I presume. Well, the topic of this day is about 3D printed bridges. And I have to be honest, this is something that I have to take the opportunity to give a huge tribute to my father. My father, I took some pictures this morning about this studio of my father, a real scientist, and I owe him this aim to challenge to technologies, to futurism. He was a real inventor with a sense of technology very romantic. I will introduce you to the museum of my family in his studio, because is the story of 3D printing. The bridge started far beyond in the time when my father used to be an aeronautical engineer and used to be the right arm of Corradino d'Ascanio, the inventor of the helicopter and also the inventor of the famous Vespa scooter. In this museum of our family, there are an amazing series of very rough preliminary prototypes. I belong to a gender of people who deserve their life to developing working, hopefully, prototypes. Here on the left, for instance, you see a very first attempts to develop a cinematic of a tilting vehicle that later became a scooter of Piaggio called MP3. You see, my father used to develop completely on his own, without help, electric scooters, outboards, and his brother was involved into missiles because had a stage in the United States in Pasadena with Werner von Braun. So this is the environment into which matured the idea of a 3D printed bridge, and this is the very important slide that from which everything starts. This is the design of the Ponte Mezzo bridge in Pisa that was rebuilt after the World War II, because after the bombing by the Allied forces. It is a beautiful bridge that my father designed with the most challenging method of calculation. It's even quite challenging to apply today, applying the theory of plasticity, a method that apply to exploit in the maximum way the properties of the concrete. This was a bridge that was inspired by a previous bridge built in Rome, the Risorgimento Bridge, that was designed by François Hennebique, the inventor of reinforced concrete. And so there is a sort of continuum between the 3D printed bridge and the story behind. And what about myself? Trying to mimic and to follow the footprint of such a big genius of technology, trying to make my own path in technology and making an incredible series of mistakes and attempts, exploring in my way the fields of robotics. Maybe nobody knows, but the 3D printing into architecture start from the footwear industry, where I used to be involved until the invention of the 3D printing. And why I invented this? Because in the footwear industry was a quite new and fascinating device, a 3D printer developed by ZHA CODE. This method, invented by Emanuel Sachs and other people at the Massachusetts Institute of Technology, was the most intriguing device I ever met in life, and willing to propose and to become a reseller, a dealer in Italy of this machine, I gave a presentation exactly to Piaggio, the factory where my father used to work. And that morning, I had the idea that scaling up this process, that is a powder deposition process, this process properly scaled up might be used to print buildings. This is the idea into which later I devoted all my life to make it happen. And as an engineer, when you want to make something related to building construction, as a starter, you print up a cube. So to do so, because I was at KUKA integrator and I developed what I used to call a post-processor, an offline simulation system that was lately used as a standard by KUKA, we printed a very first cube. I want to share with you this video that is related to probably the very first 3D printed item for architecture or for building construction, merely, banally, a cube that we printed in Tuscany in 2005. And then because I was completely ignorant about what discovered being parametric architecture, having made the classic studies, I decided to print a very classic Greek column. And then when I realized that this process was too slow, in my opinion, for printing fastly, cheaply, and quickly, and buildings, I wanted to have something not having only one nozzle, but a multi-nozzle machine. So I moved toward, I abandoned let's say, the vectorial printing strategy, that is the one that is commonly applied today, and I moved toward a raster printing method called today particle bed 3D printing. So I wanted to develop the analog of an inkjet printer at a higher scale. Some of you maybe have seen several times my process, but in principle, the building process that I, let's say, invented, let's say, maybe copied by Z Corp, is made of 4 steps. The first one consists of spanning sand or gravel or any particle, creating a thin layer, and then printing the section of the image of the object to be printed on it, and then repeat the process again and again, and at the end removing the sand from the to unveil the object. And this is the most exciting part of the story, because I asked, meanwhile I was developing the 3D printer, I asked to Andrea Morgante, who used to work for Future System, to develop an iconic object to be printed. And I had in mind something like the tempietto of Donato Bramante on the Gianicolo Hill in Rome, and Andrea proposed the shape inspired by a skeleton of an amoeba, a radiolaria, that became a sort of gazebo. And in the June of 2007, we attempted to go and print directly on site the radiolaria. This is just a rendering, but unfortunately, the company with whom we partnered to get the binder never provided us anything. So I had to dismantle the printer and bring indoor. And I developed the printer, the binder, despite I'm not a chemical, adopting an abandoned bonding chemistry called Sorel chemistry based on magnesium. And this way I could realize a sandstone made of magnesium oxide and magnesium chloride. You might wonder why you don't print concrete, because at that time I was so freak and hippie and in love for adopting novel bonding chemistries. Unfortunately, this is a chemistry very delicate to apply, and I didn't know at the time the existence of the geopolymers that I use today. The morning of July 2008, I printed with my brother Ricardo the first layer of this radiolaria structure, and finally we realized the first 3D printed structure. And willing to scale up immediately the radiolaria sculpture, we scale up to 8.5 meter height. Apparently the municipality of Pontedera accepted this work, and we work hard to print in 3D this structure sub-partitioned in building blocks, being quite difficult to print in one go on a roundabout, but unfortunately was never given the permission to place the radiolaria structure on the roundabout. In the meanwhile, as Neil mentioned, I was absolutely struggling to showcase the first 3D printed home. This is a sketch that was made by James Gardiner, an architect that was introduced to me by Mark Berry, the engineer-in-chief of the Sagrada Familia, because at that time I wanted to print something as a tribute to Antoni Gaudí. That's why I went to Barcelona. And we suppose and we hope to print the entire building structure to be assembled in Sardinia, in Porto Rotondo, but again, the landlord used to own just the land, but not the money to afford the expenses related to the realization of the entire building. So basically, this is a story of a wish of printing a house without succeeding, almost never. Except one time, 1 year later, when La Triennale Museum commissioned to me a very basic concept of a 3D printed house. To be honest, I dislike this approach because 3D printing is a means to create amazing organic shape. But the architect said, no, Mr. Dini, I want to say that we print houses in one go and we have to make something extremely simple. And this is the reason why in November 2010, we delivered this tiny home. I don't know if can be considered the first 3D printed home. In my opinion, it is indeed, despite only hunters has been attending this tiny home on the top of a hill in the nowhere on the Apennines close to Faraneto, in the Piacenza Apennines. And then, as Neil mentioned, I started to make a lot of experiments in different fields, space, using lunar soil has been a project incredibly successful, despite I was somehow a project of minor importance compared to the wish of printing homes on the earth. But the collaboration with Foster and Partners was successful as well. Probably the first thing I ever did in life that has been applying this technology to print artificial reefs. Again, this idea of printing reefs is not floor of my bag. It comes from James Gardiner, who, intrigued by the potential of this method, proposed me to save the Great Reef of Australia by printing reefs. And so we did. And this is there is a booming market about 3D printing. I can proudly say to have printed the first. And not so proud as well, printing a shelter for anti-ballistic purposes for the military army is just an achievement, is just a priority. And finally, let's come back to the bridge. Well, I was approached by a Chinese company and also by a Dutch company among the several who was asking to me to print ships in 3D and any gender of structure, but the one that was asked me to print a bridge in 3D to get, let's say, to make a feasibility study was the most intriguing, because you know why I was intrigued by the possibility to print a bridge, because my father was very close to pass away at the time. In fact, he passed away in 2015, and as a tribute to his memory, because before he died, I made some studies to make an organic bridge. And basically, the concept was to print the bridge with very lightweight material and bend the bridge with the fiberglass textile, or even better, basaltic textile. We made very small attempts printing chipped wood and bending with basaltic fiber. This was just an exercise that remained dormant until we had the opportunity to enter into collaboration with Acciona in Madrid. Acciona was approached us in 2014. The initial idea was to print artificial reefs. I was pushing heavily for doing that. Acciona asked for a custom printer, more automatized compared to the one that we did before. And to comply this need, we made a machine that is, we can define like a super gigantic Z Corp printer, a machine with an incredible system to lift tons of sand. Acciona opted to use not magnesium chemistry, but a mortar of Portland cement. And in November 2015, we moved the printer purchased by Acciona to Madrid, and finally we started to make the very first testing, printing again for testing cubes. And this is how the story began to prepare the object to be printed. And when Acciona asked me, Enrico, what would you like to print? What would you suggest to print as a first object we are going to print? Well, as a provocation, I said, why don't you print a bridge? But Acciona was not confident with organic design. Acciona is an engineering company, they make straight things. So I suggested to approach IAAC, where I have a lot of friends. And this is how the contact and the collaboration between IAAC and Acciona began. And since then, I make one step backward, because Acciona knows what parametric design is. I was updated by what's going on about the bridge, and the first blocks. Despite I was willing to print the bridge in one go, I had to accept the idea that we might print in sections. And here you see the section of the bridge and the pre-assembly. And finally, after a couple of years work, since the beginning of the design of the printer until the full testing of the printer printing the bridge was placed. And this is the end of my presentation. What we do today, I'm in love for artificial reefs. This is my main job today. We are having a good success in Hong Kong, where we deployed recently a set of basic artificial reefs, but with an amazing smart foundation systems. Thanks for your attention, and I give the word back to Neil.
Enrico, thank you. That was really charming. It was really beautiful to see. I didn't know all about your father and his pioneering work in other fields, but it was beautiful to see that and to see the story behind the bridge. And I didn't know about that small little hut that you, well, it's a building which you have in Apennines that you put there. So I found out an awful lot there. It was beautiful to hear the story behind it. Really, very beautiful and very touching. So we move on
Thank
to
you.
Rodrigo, who was working as a computational expert within the team for IAAC. For those who don't know, IAAC is the Institute of Advanced Architecture of Catalonia, an organization I think was started around 2000, 2002 or something, that has become a real sort of pioneer in many ways in promoting technologically advanced progressive design. Rodrigo, would you like to share your screen?
Yes, of course. Give me a second. Okay, does everybody see my screen?
Yes, fantastic. Okay.
Perfect. Thank you very much for the invitation, Neil, and glad to be here, even though that Areti couldn't be here. She asked me to fill in her shoes, trying to fill in her shoes. But thank you for everybody to for the invitation, and indeed was this collaboration that we did with Acciona back in 2015, I believe, that we started working on this, was the first time that we were actually working in a project such as this. And obviously my involvement in the project was purely in the computational side of the bridge, but so most of my conversation will be mostly the process, the computational process that brought the design of the bridge all up until construction, because we were talking a lot with the engineers from Acciona. But basically, we were asked to design a 12-foot long footbridge in Castilla, in Alcobendas, in Madrid. And well, it consisted in a 3D printed micro concrete modules that were 2 meters long and with 1.5 meters wide. And well, the whole idea, as Enrico mentioned, is to take advantage of the opportunity to use this kind of technique, this 3D printing technique, to free ourselves from straight lines and be able to create more organic and porous shapes. Now, this brought a lot of challenges in order to design and build. So we were working very closely with the engineers from Accionas, going back and forth. And basically, the biggest challenge was to deal with these complex geometries, in which they had to be boiled down to very simple modules that they can be then calculated in 3-dimensional shapes with ANSYS, for example. So it brought a lot of pieces trying to come together, mainly in the design, the computational design development. We divided it into 3 main aspects. The first one was the topological optimization for material distribution, because we wanted to make it as lightweight as possible and distribute material only where it was needed. In order to create the porosity afterwards, we tried to add vectorial agency. So in this way, they would actually create this flow as a tractor, and later on be able to use that in combination with mesh wrapping morphology in order to close up the design. So of course, being a computational designer, specializing in parametric design or algorithmic design, allows us the possibility to go through many iterations. So of course, we had to go through many of these catalogs in order to to see which are actually the possibilities that we could actually achieve. To achieve this kind of texture, these porosities, these elements that actually they had a lot of constraints, but at the same time we had to take advantage to be able to produce. So you can see how by playing with these kind of flows, we were able to get that that surface over the stone, which in the end it looks very organic and almost natural, you know. Now, originally, I like to show this image because this is where we were confronted with the reality of the situation, being the fact that this had to be a bridge to be built in the public space used by pedestrians. So of course we were ideally we wanted to create a one continuous form in which we had much more light shapes, but clearly this couldn't be the case. And of course we were at the same time in the site of Acciona. They were actually researching and testing this new material that they were working with, which is microconcrete, and they were trying to see in which direction as well that we needed to print. So obviously doing testing, working with UPC so they can actually get the actual numbers, and obviously the testing you can see on the right side of the image, how the different tests would come out, sometimes would come out with errors. And so obviously this was great help for us as a feedback to regenerate the shapes and control how are we gonna print it. So of course, being the first time that we are doing this kind of project, and being an executive project as well, we had to embed structure. So for two reasons, one being a public project, so it had to had a specific structure that we were allowed to use. And secondly, because that the modules it was divided into 8 modules that it could fit the machine. So we embedded it with structural elements, and of course thinking about how it can be anchored to the floor. So by the end, this is the final design that we were actually able to mix both all the needs that were required from the Ayuntamiento of Alcobendas and the engineers from Acciona, and of course from IAAC as well. So obviously the very interesting part is how they actually produce the whole bridge. It took around 2 months to produce all the necessary pieces. They were actually bringing them to producing them in Acciona and then moving them into a different location, so they could be actually be placed, stored, and put together. You can see in this small video right here about how they're actually transporting all the pieces once they're all put together in one piece directly to the site. So like I mentioned, the project itself was around 2 years, 1 year and a half, 1 year of design, let's say, plus 2 months of production, and only 2 days to locate it in site. So obviously there's a big conversation about the methodology of 3D printing and how in terms of production, and how can be located in place, being treated more like prefabricated pieces and brought later to the site. And finally, I want to finish off with this image. This is a more eroded picture that is back from, I think, last year. And what I love about this picture is you can see how the natural elements have been influencing over the bridge, and it's getting old. And I think I like it a bit more now because it looks a bit more natural. But overall, it was a great experience. And I think that for the challenges that Acciona had to face, having this new machine based on the technology of D-Shape, it's impressive that they actually were able to do this. And in a matter of saying that they actually set the standards for the up and coming projects for the later future. Thank you.
Rodrigo, thank you. That was also fascinating. There's a whole story there that I didn't know about, and that's incredibly interesting. I really think, Philip, that we should be making a book out of this, because this is fascinating to hold this. And I think what's interesting is that, just to say that just as Berojos Neves and Enrico Dini didn't know quite what they were doing, what each other was doing, even on the space thing, so we didn't know what was going on at IAAC. And in fact, Philip thought he'd 3D printed the first ever building, first ever bridge. I pointed out that it wasn't, it was IAAC. But it's absolutely fascinating to find out about those things. So thank you so much. So I want to just say one final thing before I hand on. And that is to say that Enrico, I don't know if you picked up on Enrico Dini's reference. Famously, back in 1850 something or whatever, one of the great British explorers, a guy called Dr. Livingstone, was in what was then Rhodesia and Zimbabwe. And there was an American journalist who came to search for him in the middle of Africa. And when he finds him by Victoria Falls, the expression he says is, "Dr. Livingstone, I presume." That was exactly the comment that Enrico made to Berojos Neves, Dr. Berojos Neves, I presume. Anyway, it's great to see these people, everyone coming together on this platform to hear the full story about the history behind these historic events. So the next, I'm delighted to be able to hand on to Philip Yuan, who I think has been producing an astonishing series of bridges. Whenever I show them to my colleagues in the States, they think it's some kind of Photoshop, as though these things haven't been built, but they have been built, and there's a whole series of them, and they're full scale, and it's historic to be able to see them today. So welcome, Philip. Yes, Philip, please go ahead.
Hi everyone, can you see my screen?
Yes.
Okay. Hello, all the friends of DigitalFUTURES. It's a great opportunity to meet Enrico tonight because we actually learning a lot very long time ago from your practice. I think different generation has different things in the history. So today I would like to briefly introduce the topic form and forces, designing efficient expressive structures through the bridge research. I'm a professor teaching in architecture school and has devoted my past 10 years engaging into the architecture intelligence and robotic fabrication. Meanwhile, when we playing with all kinds of advanced robotic technology, in terms of the gravity, when we design the buildings, I found this significant correlation between the structural performance design and the robotic fabrication. Therefore, shall we say, robotic tectonics is a kind of representation of the form and forces. In 2015, my office actually, we designed and developed this installation, this special platform, 18 axis with 2 robotic schemes and collaborate with each other. And then we start to make further research, macro scale, which could be approach to different research scenarios. And from 2017, after we have the robotics 2 years, we start to make research on the bridges. So we focus on the bridge design in the architecture school. Obviously, it's very it's good to stay naive, because the architects normally at the very beginning consider the formation of the bridge as the form, while it's mattered nothing to structure at all at the very beginning. So the first year in 2015, we put forward idea and try to directly printing the forces flow. But unfortunately, if you see, I missed one of the image, because this bridge in 2015 broken down after 45 days of construction. So we certainly understand the structural performance matters, the safety rather than the beauty at all. And in 2018, we implement, the first year we implement not concrete printing, but this kind of a plastic, modified plastic, which could be printed more light and compared to concrete. And second year, we start to use the welding, the steel welding. It's even stronger. So you can see we can stand like 7 people in the second year, and it's lighter compared to the first year. And the third year in 2019, actually we test this kind of composite structure system, including the welding, steel welding as a bone supporting system. And also we introduce carbon fiber and glass fiber as a substructure system, the handrails and the stairs. So it's like a composite structure system, and we can stand around 20 people on the bridge. So you can see a lot of our friends, including Philip Yuan, Mark Burry, Mike Xie, and a lot of people coming to Shanghai yearly, including Andy Clark and Neil Leach standing in the middle. So it's 2019, give us a special memory. And 2020, because of the COVID, we narrowed down the scale of the bridge. And actually this year, we start to test concrete printing. So it's like the contour layer contour printing in 2020 is still a bridge. And then 2021, we introduced UHPC, which is a very high performance material as the main structure supported at the bottom. And at the same time, we introduced plastic printing as handrails and stairs. It's also a composite structure system and can standing around 25 to 30 people on it. So this is last year, actually, we introduced for the bridge. And this year, 2 weeks ago, we actually test the contour printing by robotics, but actually the printing technology is actually follow the force printing, and actually it's also it's a compression tension structure, collaborative system, and have very high performance. We're want to test an even bigger scale at the end of this year. So that is just the bridges as a research process for the team. And the next, I would like to specially introduce the studio. Last summer, I was invited as a visiting scholar, visiting professor by RMIT Architecture School to lead a Master of Architecture Design studio. The studio explores the potential application of 3D robotic concrete printing as a structural prototype through the intelligent computational design in the process of architecture design, and aims to improve the additional manufacturing technology, especially at a large-scale concrete 3D printing technology. And I also collaborate with Nick Bao, who is a lecturer teaching RMIT, and we teach together all the students, RMIT students. They actually stay in China because of the COVID, cannot go back to Melbourne. So it's all the students and also the teaching assistant with us. At the same time, we invited different interesting lecturers into the studio, including Wang Xiang, who gave a brief introduction to the students. The topic is about the gravostatics in bridge structures. And also we invite Mangsat, who is from the University of Pennsylvania, who actually the PhD student of Philip Yuan, and right now assistant professor. And he actually introduced the polyframe. He actually invented a Rhino grasshopper plugin polyframe, which introduced the 3-dimensional graphostatics to the designers. And at the same time, Nick Bao, who is also the student of Mike Xie, who introduced Amoeba as a special tools to update bi-directional optimization of the ESO evolutionary design, structure design, topological design. At the same time, we also introduce the FU Robot, which is an in-house developed software by my office, and Lu Ming is the PhD candidate and helped me to develop the software right now. And also Li Ming Zhang, who is also a PhD candidate in Tongji, introduced the working flow, how to integrate the structure performance design and 3D printing technology. And Yan Chao also introduced the Rhino and the Grasshopper as a teaching studio content. So this is all the students, and we actually, every student designed a bridge and also 3D printing them in a small scale, 1 to 20. At the same time, we print a mock-up, a part of the bridge as a mock-up, 1 to 1 scale in the courtyard of the office. So I think in the 3D printing, I think structure performance matters. And the most importantly, I think graphic statics is a very ancient technology, actually, which can date it back to the Renaissance time, when Da Vinci also expressed in his manuscript the idea of reproducing the magnitude and the direction of forces by means of the line segments. And the German engineer Karl Kalman, who also named as the graphic statics, the father of graphic statics, and he actually played a very important role to set up the technology. And the Swiss engineer Robert Mliat, who is a pioneer in application of the graphic statics and designed the superlight and the famous bridge, and make full use of concrete as a compression material. And another Swiss engineer, Jörg Konzert, who actually graduated from ETH in Zurich, and also he introduced the principle of graphic statics, transform the force flow into the elegant pedestrian bridge. I think it's all the inspiration we can take and can learn from them and implement into the robotic concrete printing. So the most exciting development of graphic statics is a three-dimensional extension of this. And the fully three-dimensional extension of graphic statics would create a new possibility for dealing with the complex 3D structures and during both the design process and structural analysis. So in the form finding method, every phase of the forces relate to the edge of the form, and the magnitude of the forces is equal to the area of the connecting faces. And we can introduce different kind of platform developed by the different structure engineers and structure office. And we have introduced a very important one of them is Polyframe, who is developed from the Mansard from University of UPenn, and also we invite him to make a lecture to all the students, introduce this special software. And also we have some other 3D graphic statics, Philip Block, and also like Onigan, also developed some other platform. So it's all the students in the studio actually, we implement the 3D graphics study to design a bridge by each of them in like 1 month and a half in the graphic statics. So these are the students' bridges, and also 3D printed 1 to 20. And in the design process, very initially with research on the book by Alan, and the students are able to get clear idea with the forces and the form. And learning from the practice, students starting their forces study journey by designing the truss system two-dimensionally. And before, one designing structure is often shown as an analysis to the form, but with help of three-dimensional graphic statics, we're able to design the forces firstly and use it as a form-finding methodology, which reverse the thinking pattern in the design process. with enough knowledge from the previous forces analysis, the students tested three-dimensionally with the polyframe, the program which showed them the potential to design in collaboration with the software. And also the architecture school students can collaborate with a toolbox and learning different structure knowledge through this platform. So these are some two of the best works from the students, and this is one of them. And the concept can be seen. Design as bridges is a practice that students did a smaller scale, explore both structure and analysis and aesthetics. So this is the iteration, how to test a different form by playing with the force diagram and then transfer them into the form of the bridge. So the concept can be seen in the plane of the shape and forces diagram as three circles in the middle. So the students' work starts from the radical force diagram to form a unique bridge structure with a circle in the middle, and then optimize the force diagram by increasing the number of the radical center in the middle of the form, a unique structure with the three tangent circles. So during the design process, the form of the forces diagram was continuously adjusted to change the shape of the diagram. So these are the different generation. Actually, the students optimize and playing with so the bottom is the force diagram, and the upper is the form diagram. So it's kind of translation, understanding the forces through the pixels of the forces. So these are the looking into more details in the design process. When designing the compression-only bridge, the students designed a 2D pattern, which will be the members of the form later, and exact it as a polyframe geometry. And later, we can find the special faces of the force diagram and generating the form based on the equivalent and optimize it with the magnitude. So the students also sought to produce the change in form from the vertical as a way to produce a skeleton like the structure. So these are the process leading to from different steps, how to design through the three-dimensional graphic statics as a compression-only bridge and through the design process. So these are scenarios, how to put them into reality, as how to re-understanding the bridge by the concrete in the natural scenarios. So these are the details of the bridge. So the top is the force diagram. The model, the middle is the form diagram, and the bottom line is actually the real bridges. We materialize this form diagram into the bridge form. So these are the bridges in the different design process. So we have 13, 14 students, and every student actually learning this kind of structure performance-based design and re-understanding why we use 3D concrete printing. It's not just about robotic technology. It's not just about the beauty, but the structure matters, the form, and why we should implement robotics to print such kind of bridge in the future. That's not finished, because we need to ask a student to test if the bridge is strong enough as a structure object. It's not just about aesthetics, which is about structure. So we test the load on the top of it, 15 kilos, and also we're handing the load 10 kilos at the bottom in the middle of it. So you can see the testing process of each bridge. With all the bridge should test by the loadings. So the most outstanding, the shape and the loading ability, two of the best bridges by the structure performance. At the same time, we find it's extremely beauty at the same time because the beauty is coming from the structure, the forces flow from the students' research. And afterwards, we trying to introduce the fabrication technology into testing the details, the mock-up of the part of the joints of the fish bridge. So we're taking a special joints which actually critically talking about the if the bridge is not totally compression. At the same time, we need some side tension forces if it could be cantilever or could be making the joints possible. So we take our courtyard from my office as a mock-up test, and you can see this is a process. We actually implement the polyfilm again to research on the details, which is about the geometry of force diagram and extending all the support points and the testing the from two-dimensional diagram to three-dimensional forces diagram. And then from the objects on the top here, you can see which is the initial forces diagram of the three-dimensional installation, and the bottom is initial form diagram to represent the initial forces of this special installation. So this at the same time we test again to the working flow about this force diagram, form diagram, and actually after iteration to make the form more reasonable at the bottom, and we need some connection joints, and so the most important of design to simplify to the minimal elements in order to represent the second form of the installation. And then we're testing the concrete printing because students, it's the first time for them to make use of them. Although the machine already developed, but students need time. They spend almost 2 weeks to understand the material, the concrete. And then we test the special mock-up, 1 to 2 scale, about the special joints. We need some tension to connecting different components. So in order to save the materials, we also introduce amoeba to reduce the concrete material. We should use as small amount of concrete as possible to reduce the concrete implementation in this installation. So this is the amoeba. Although we can find from the 3D graphic statics, and then we introduce amoeba as a second plugin, which is the hybrid authorship I introduced to all the students, because the future architects, designers, you may not have the very deep knowledge of structure analysis, but you can collaborate with different toolbox. So I name it a kind of hybrid authorship. The architects can collaborate with different tools. So the first step is about the polyframe. The second step, we introduce the amoeba to the students. And third step is the FU robot, which is a robotic printing platform. The students can printing all this kind of form in a very short time. So these are the objects after optimization. And also we introduce some structure analysis by Karamba, which is another software platform, to prove if all the structure is safe enough. Because this is a discrete system, we have different components. But at the same time, we should test if this kind of connection is safety. So this is the initial form diagram of the forces and the components. So the physical intelligence or the material intelligence actually embedded into the forces flow and embedded into the structure optimization. So the robotic concrete printing is not just about the concrete and not just about the robotics, but the structure performance matters a lot to the future robotic printing. At the same time, we have not only the compression, we also have tension because we have cantilever. And then we introduce this kind of cables for the tensions to keep all the structures safe. And then we subdivided all the components of this installation. And the most challenge for the 3D printing is not parallel counterline printing. You can see the height of each layer of the 3D printing is all different. So it's a very high advanced test for the team because we need to scripting all the two paths in a very accurate way, and also why we introduce robotics to print not 3-axis CNC, because the robotics have 6 axes, and then that will help to print this kind of multi-height contour layers. These are the components and how to put them together. So we design all the drawings carefully with some steel connections, and which is accurately 3D welding and by the laser cut, and then we embedded them into the concrete. So these are the two paths of the 3D printing we generate by FU robot. And then the students spend a long time for all the drawings. They have no research background, but they should learn in 1 semester how to print it. These are the drawings in the mockup, and these are the machine and the components printing. And we're testing a lot for the failure, but actually it's very good for the students to understand the material performance and the materiality of the concrete. So these are the two paths which generate by the FU robot. And then not only each layer of the printing is changed, but also the height of the print, and also the perspective of the angles of the effectors also rotate through the printing process. These are the printing two paths we research. Is not parallel, you notice. It's changing the height of the printing layers. And this is also simulate by the FU robot simulation of the printing two paths. This is the printing process, and also the joints for all the discrete components. And students, the learning in the whole process. These are the assemble process in the courtyard by all the students, and the 2 professional workers help them to teach all the students how to put them together. So all the components was fit into the site and assembled in 3 days. It's very fast, and also the prefabrication discrete components are put in different location, and also the tension of the steel wires, and put all the components together. So these are small models. And the final object installation. The students are very happy. In around 3 months, they're learning a lot, from the structure performance design to the implementation of robotic concrete printing as a structural object. And at the same time, introduce, I was invited as a visiting professor in MIT, and I'm co-teaching with Philip Block as a first book, robotic force printing. And second, I was invited as Thomas Jefferson Professor in UVA, United States, and matter aggregation. We introduced the timber robotic fabrication. And third book is coming this year. The topic, the book name is Intelligent Force Printing. So welcome to notice to read these three books. At the same time, it's not just about this small bridges research. My office also doing some macroscale 3D printing. This is plastic printing. We did 2020 during the COVID around more than 2,000 square meters surface. So at the same time, last but not least, I want to introduce the journal we just developed, kick off last week. And the name of the journal is Architecture Intelligence, which published by the Springer Nature and collaborate with Tongji University. I'm the editor-in-chief and also invite Professor Wu Zhiqiang and Neil Leach as the honorable editor-in-chief. And also we have academic committee, including Areti and Matter Thompson, Philip Block, Max Xie, Aki Mangus, and Tong Xiaohua, Professor Tong Xiaohua from Tongji. And also we have the editor, Caitlin Muller from MIT, and Yupeng Wu from Nottingham University, and Wei Xinhuang from Tsinghua University, and Jianling Liu from Donghua University. So expected the first issue will launch, and the date will be the June 2022. So looking forward for this special journal, Architecture Intelligence. At the same time, every year of DigitalFUTURES, we organize CDRF, Computational Design Robotic Fabrication Conference. So this year, the topic will be the hybrid intelligence. So over the past 2 months, we received 100, today is 113 abstracts. And after the abstract review, we also welcome to call for the full paper directly. You can turn in the full paper before 15 March 2020. So these are the 3 books. Actually, we published 4 books collaborating with Springer publisher. Springer publisher is not, I think it's more about the building technology and the architecture technology. So, and this is blind review conference, and welcome all the students and researchers to turn in your research papers, and also all kinds of evidence-based research will be welcome to publish on this platform. Thank you to everyone. Thank you.
Thanks, Philip. That was fantastic. Just to Enrico's terms, this was like a Janus-faced presentation. Janus being the Roman god of entrances, who looks both ways, forward and backwards. And I think this was an incredible overview of what you've done in the past and of what could happen in the future, what will happen in the future. When you refer to those books, I can't help but feel that this session today should turn into a book, because there's so much that's been revealed about the background research that's been going on behind this. And I just want to emphasize Mike Xia's and also Philip Block as being some of the crucial people who've been contributing towards this. They're in the background, but they're highly significant. So that is a good segue to introduce Shajay Bhooshan. Shajay needs no introduction, I don't think. He's certainly very well known to the DigitalFUTURES community, and he's going to talk about a bridge, which is a collaboration between the Block Research Group at ETH Zurich and ZHA CODE. Welcome, Shajay.
Thank you, Neil. Let me share my screen. Can everyone see that?
Not yet. It's still, it's started, but hasn't appeared.
Do you want to try again? I can stop your share.
Yeah, maybe.
Yes, you can try again.
Okay,
Yes,
we
we're
can see it
good.
now.
Yeah. Shajay, you're on mute.
Yeah, thank you, Neil. Thank you for the introduction. And as you mentioned rightly, it is a historic session, and it's kind of hard to follow in at the end of like this series of presentations. But I'm going to try and talk about Striatus, which was a joint collaborative design, engineering, fabrication, and construction effort between Block Research Group, ZHA CODE Architects, Incremental 3D, and Wholesim. I'm going to represent all of them, but like in my dual role, one as a PhD candidate at the Block Research Group and also as head of ZHA CODE Architects Computation and Design Group. So Striatus is basically an arched, fully unreinforced masonry footbridge. Why fully unreinforced? There is no steel, there's no reinforcement in neither the printing ink nor inside the blocks. And it follows a masonry logic, and it is assembled, dry assembled without mortar. We believe it is a milestone in like in a responsible design, and I will take the next 10 to 12 minutes to talk about why we believe so. So what were the goals of Striatus? Like, and this was a project in 2021, last year. And so when we set out to make this prototype as part of the Venice Architecture Biennale, like not the which is a collateral event organized by the ECC. What we set out to demonstrate is that 3D printing is indeed matured enough that like we can now begin to show how like 3D printing can play an essential role along with other maturing technologies to responsibly use concrete. So to combine one of the most ancient materials and also ancient techniques of design to demonstrate that like low energy, low carbon, thin, lightweight structures are possible, which not only have like high strength and can span large distances and can also be high endurance. So in this, like again, this is not anything new for any of the regular Digital Futures audience. Like Block Research Group has been pioneering attempts to bring like this knowledge historic that is embedded in historic architectural construction and design into the 21st century. So this historic Gothic vaulting techniques, etc., already are examples of such a high performance shape. So whereby like if you with designing the shape appropriately, like using curvature and development of form, which is elegant and aligned with the expected force flow, you can significantly save material. And so that's one of the key messages of Striatus is that like as Philip Yuan already explained in depth, like there is a relationship between form and forces, and which ends up saving us a lot of material. And this has also been previously demonstrated in the 2016 Venice Biennale, like where the Block Research Group made this spectacular thin stone vault. At parts, it is only like 10 centimeters thick, and it clearly spans a large amount of distance. And so Striatus, like coming 5 years later, is trying to combine the historic masonry techniques, which have been upgraded through digital means and new knowledge and new information and new computational frameworks by the Block Research Group. And we wanted to combine that with the maturing technology of 3D concrete printing. So in that sense, like the historic location of Venice also provided added context where we wanted to extend the previous armadillo vault with 3D printing, 3D concrete printing, and inform 3D concrete printing with masonry. So the two main goals that we wanted to demonstrate was that there is a new language for concrete that is possible, and whereby it's a new language for an enduring, very established material that is widely available across all of the world, and combine that with ancient wisdom of masonry, particularly unreinforced masonry, construction and design, and new digital and robotic technologies to demonstrate that a material that is widely available you can design responsibly with concrete. And so that was the second goal, that sustainable digital concrete, where we wanted to show that concrete combining with digital technologies of design and manufacturing we can demonstrate a pathway to reduce the amount of concrete, and also demonstrate a pathway to show structures that can be repaired and could also be reused and then also be recycled. So these were the two main goals, and we set out to achieve them through three pillars of parallel efforts, which one of them is strength through geometry. The second of which is integrated computational design and construction. And the last of it is robotic 3D concrete printing. So starting with strength through geometry, what do we mean by that? It's maybe most eloquently put, articulated by Eladio Dieste last century, where he articulates that resistant virtues of structure that we make depend on their form. So it is resisting force through the shape, and not some awkward accumulation of material, and particularly not the awkward accumulation of high strength material, which is what we set out to try and do. So the bridge itself is composed of a central deck, which is completely in compression, and it prevents 6 arches from falling inward. So together they form a kind of hybrid, a composite masonry structure where the arches and the deck act in unison. And the resultant forces the thrusting forces at the foundations are kind of negated by having a tension tie that ties all the feet together. So that is a simple logic of geometry through which masonry geometry through which we resist the forces, and so thereby the amount of concrete used can be very highly reduced, and thereby also we can ensure that dry assembly and all the other benefits of unreinforced masonry paradigm can be achieved. So it's masonry at 2 main scales. One scale is the assembly of dry assembly of 3D concrete printed blocks arranged in arch and vault-like shapes, and the other is at the scale of the 3D print itself, where the plane it's non-parallel and inclined plane printing, so that the print layers are orthogonal or perpendicular to the expected force flow. And that's another method by which we can fully activate concrete and potentially use much lower strength concrete, because concrete is much better in compression. So these are 2 scales by which at which masonry is operational in the project. So the second bit is integrated computational design and construction, which maybe I will take a little bit more time to emphasize that it was a truly collaborative effort, across design, engineering, fabrication, and construction, all coming together from day one. And it's not that architects design something and then the engineers had to engineer it. So it is representative of the 21st century way, perhaps, of designing in a collaborative way, so that we can tackle the various issues facing the construction industry. And also it's about like the tooling, like it is very task specific and effective. It is not like it is simple but bespoke tools that we had to create because existing tools are neither aligned with digital design nor with robotic production, again, as perhaps maybe highlighted by Philip Yuan. And lastly, like our tool set like is also very open source, and it is one of the basis of collaboration and like perhaps even extension in the future. So everything that we learned will be published through research papers and assimilated into the Compass research framework. So this framework allows us to extend, on the one hand, like design-friendly methods, which concrete 3D printing definitely needs, because so far in the last 30 years, all of the effort has been on the material technology and the robotic process technologies. And in that sense, design has been somewhat neglected. So we need design-friendly tools, and at the same time, those tools need to be aware of production, what the robot needs, how the material process happen, etc. So we came up with a workflow that allows designers to design with like easy to manipulate like control mechanisms, like simple graphs, and along the way it can in the background we can create all the geometry for fabrication and construction. So we simply start with the center line of the deck, which went through many manipulations, and subsequently we use well-established mesh processing pipelines, like to kind of thicken the center line of the deck, and then subdivide that, and subsequently find an appropriate shape for the deck, which is where like the idea of Rhino Vault and thrust network analysis plays a key role, which allows us to find unreinforced masonry shapes. The global form is in complete compression and therefore doesn't require any steel. And subsequently, like we also develop tools and algorithms and like tool sets to discretize the geometry into blocks. There were 53 blocks, and the so-called stereotomy of the bridge. And so these steps like went through many iterations. It's not just one click step, like many processes, many iterations of the bridge. And then in each iteration, there's also testing using so-called discrete element analysis to consider the load-bearing capacities and also the rigid body dynamic behavior, and if the blocks are in rigid body equilibrium. So, and you can also notice all along the right through each one of these steps there, we are keeping track of like the various information that is added to the file, the exchange file that it is transmitting between various teams. And so this is our method of communication and method of collaboration. So all in a very simple to transmit and simple to read and write file format. And once we know of the global discretization and like the global form finding, we then develop the print paths where we design the blocks to locally be perpendicular to the expected force flow through the blocks, both the balustrade blocks and the deck blocks. And each of the blocks has its own unique set of print paths, and altogether there were about like 7.5 kilometers worth of print paths, that were computed in this way. And you can see it is also hollow, so it is also kind of locally topology optimizing to place material only where it's needed, so thereby saving more of the concrete. And so this process is repeated over all the 53 blocks, and which are then printed and assembled on site. And so the process that I just presented here in a linear way, actually it took 6 months across 3 geographic locations in London, Zurich, and Innsbruck, and had added to the burden of like the pandemic. And so 6 months start to finish, from design to production to construction, and along the way there was Joe Biden, who was visiting Venice, and like we had to shut down the construction site for 3 weeks, and plenty of other unknown things that crop up. Like, so there's the integrated design and engineering framework is testament to the flexibility. Like, so the flexibility that it offered was instrumental to cope with like all of these disparate processes, and to unify them into a kind of smooth integrated design to construction pipeline, and also to deal with unknowns as they pop up. So lastly, like the robotic 3D printing of concrete, like this video might not do enough justice to the digital craftsmanship of incremental 3D, but like I hope you can see the extreme care and concern, like and craft they bring to this process. Like, it's extremely well finished, like straight out of the process. There's no post processing, there's no post finishing. And so that's one of the features of 3D concrete printing, is that it is inviting craftsmanship back into the construction industry. So and the fact that like their production pipeline actually talks to the overall design to construction workflow, and it's deeply integrated, is also a essential feature of such collaborative work, like that the fabrication side of the software talks with the design side and talks with the engineering side from day one, and not in a linear way. And so one of those benefits of that was like this particular groove, which we discovered like when we did the first test print, that it wasn't designed to have that groove. It's just that the robot has to turn, and when it turns, it goes slow. And so when it goes slower, like there's more material that is extruded there, and so it naturally creates this groove, because you want to have a continuous path of so that there's no starting and stopping. So we naturally had to account for this groove. And so what we did, we incorporated that into the design process, so that we just made sure that like these grooves are aligned, they occur exactly in controlled ways across each of the layers. And so the other such feature was like every time the infill turns, it will produce a groove on the outside, as you notice. So the groove on the outside is a consequence of the infill pattern. So there are all these tectonic possibilities that we discovered because like incremental 3D was like part of the design team from day one. So that's another feature of like the contemporary design to fabrication workflows, like which opens up new degrees of expression. So finally, all of this was printed and transported to Venice, and you can see like it's only lightweight like boom mass that we need to lift all of these 3D printed blocks, and then there's a scaffolding erected, and all we need is like this again, one single spider crane, and I have to give a shout out to Theo Burgin and his crew, again highly skilled construction, which is being invited back into the construction industry. So and so 53 blocks were assembled, starting at the feet, and then building up the arches, and first the deck and then the balustrades. And here's the last keystone, and consequently leading to completion of the bridge, which opened in summer of 2021. And to our surprise, because it was in a public park, like lots of people started using it. As soon as it was open, like naturally it became part of like the the everyday life of people using this park, and which was very satisfying to see that like all parts of the bridge was actually used. And there were dogs running up and down the bridge, and then there were children running around on the bottom, and so on. So one of the key takeaways for us, like through this exercise, is that we hope to demonstrate that the masonry paradigm and 3D concrete printing is a match, a perfect match, like a plus, like forced aligned 3D printing, and then using dry assembly and fully unreinforced concrete, and also separation of steel and concrete, which is very essential for recycling, because we have these 3D printed blocks. And the tension ties and the footings are the only steel that is used. We can easily separate these two and recycle them individually. And so so all these features of the bridge, which comes because we combine masonry design techniques and analysis techniques with 3D concrete printing, allows us to demonstrate a pathway for responsibly achieving ability to reduce the amount of concrete used, potentially reusing the concrete, which is currently underway. The bridge has been dismantled and the bridge has been crushed, so it can already be used. And also potentially you could also repair sections of the bridge, because you can have temporary scaffolding, and disengage one of the blocks and insert a new one. And as I said, like it also allows us to recycle the two materials. And Block Research Group is like commercializing this floor slab, which incorporates many of these principles. And the key of it is that like the key benefit is that we can reduce the total amount of concrete and also steel used at no loss of tectonic expressivity. So that's one of the things that we wanted to demonstrate, is that a new language for concrete is possible whilst being sustainable. So with that, like I thank you for your attention, and like if I could also request to please consider nominating the project for the Arc Daily Awards, because all innovations in the AC industries needs our support. Thank you very much for your attention, and I'm open to any questions.
Thank you, Shajay. That was fascinating, absolutely fascinating. I can't help feeling that the bridge, as well as being the subject of what we're addressing here, is also kind of conceptually the way we're operating, bridging architecture and engineering, bridging academia and practice, and indeed bridging across the globe, because we have Enrico in Italy, we have Shajay in London, we have Philip in Shanghai, I'm in California, and Pavleen, who's live streaming, is in Mumbai. It is kind of, we're bridging the world. At the same time, we're going back we start off in Italy, we're going back to Italy as well. So I would like to open up to questions at this point. I mean, this has been absolutely fascinating. One of the best ever sessions, I think, of Digital Futures, because it is so focused and addresses something that really is such an important kind of question. So let's open up to some questions. Maybe I would like to start by inviting Enrico to comment on the bridge in his native country of Italy, about the way that it's gone from the bridge of Enrico's father to this very incredible recent structure.
What can I say, Neil? I'm truly admired, really admired, because if I go back to that time, I was completely alone in thinking about the endless possibilities offered by 3D printing. And I was dreaming about what next generation might enjoy these new opportunities of making new architecture. Because you know what, every generation needs to develop its own architecture. I mean, it's a way of expression, architecture. And what I was really frustrating me at that time, at least for myself as an engineer, a civil engineer, coming out from this endless indigestion of reinforced concrete, especially in Italy, that has been jeopardized most of the city of Italy has been destroyed in the peripheral with an abuse of reinforced concrete with this. So try to figure out my frustration as an Italian coming from one of the most beautiful country, but after World War II, a country jeopardized by reinforced concrete. So my comment is that I prove joy to see that this signal, this message of new opportunities has been undertaken by a new generation of architects worldwide, basically, and academics. So I dreamt for libraries of new books, and now I see the opera on the go rather than completed. But for me, I feel like a dinosaur somehow, because despite I've been handling with robotics at the very early stages, developing post-processor for robotics, now I'm just an old dinosaur, and I bless you all, guys, and enjoy the future of new materials, new robotics, new method, new algorithm, everything. You have an incredible, endless next in coming centuries of stunning improvement into architecture. This is what I think.
Enrico, you're far from being a dinosaur, although the first three letters of your name, the first three letters of dinosaur. No, but I think that his history is very important here, because I was a student at Cambridge and I was brought up with the extraordinary fan vaulting of King's College Chapel, something that I think that Philip Block refers to a lot. And that's the other bridge I think we're making, a bridge between some of the kind of the intelligence of some of the ancient structures and the intelligence that's going into the structures of today. I would like to invite Philip to maybe to maybe offer some observations on the latest project, and also on Enrico's work, which we didn't really know that much about, but thanks to today's session, it's all come out into the open. This has been such an incredibly informative session. But Philip, what would you like to comment?
Yes, I agree with Neil. I think history is important. Different generation actually testing to failure and testing to different possibilities. So Enrico, when I was a student, I started notice what you are doing. Actually, you are the pioneer at the beginning of the century, and actually play a leading roles and open a new horizon in how to construct a building by making the machine by yourself. I think not only you, but also Baruch, we also invited him to Shanghai in 2012, and he introduced actually the 3D printing technology to China very early. I think I appreciate and your contribution to the history actually of this kind of making machine, not just doing design or using the commercial machines, but actually you design a machine and actually you design the crafts and working flow. I think that's especially your contribution to the history. So because the background is different, I actually am learning a lot from the world. I think that's why New Leach and me, we set up this platform. I think the future of knowledge should be open, should be a sharing culture. We should learning from the world. Actually, the future is a kind of cross-discipline and interdiscipline to the architecture discipline, and it's really important. Actually, over the past few years, we're learning a lot. For example, from Philip Block. He is actually doing some fundamental research of the graphic statics. That is a structure engineer perspective, but actually from the architect's perspective, I think which is extremely important and give us a reason why we should implement robotics into the architecture industry, because we want the structure more efficient. We actually want to save more materials, and we want to make high performance structure system, for example. Yeah, that's the reason why we introduce the structure knowledge into the the design process. At the same time, after we implement this kind of super high performance analysis tools, we find the forms go to unlinear. The form goes to differential, goes to discrete. For example, that needs some new industry, new ways of thinking how to construct a building. So we actually, because I also have a design office and we making a lot of practice not introduced today, we actually implement a lot the robotic fabrication technology into the practice. I think the history for the future is not a revolution totally change in one day, but it's kind of evolutionary process. We should introduce more advanced new technology into the practical process. I think the history is doing by us because we want to test to failure, to test to the new possibility. And I think the material intelligence, I make a discussion with New Leach last year, material intelligence versus immaterial intelligence. Right now, the metaverse is coming where the students interested in design some virtual architecture in the abstract world. But at the same time, I think my understanding to the architecture, future architecture, should be still go to material. How to integrate the, that's why we named the DigitalFUTURES this year, the topic's hybrid intelligence, because we need to understand why the material intelligence is still very important to architecture. But that should be an integration process, how to introduce or invite all kinds of virtual things into the physical world, including the design process, including experience process, including the ways how we teach our students and how to define our industry for the future. So that's my brief thinking by the fantastic lectures from Enrico, from the Rodrigo, and from Shajay. I think learning a lot from you. Thank you for your presentation. Thank you, Neil.
Thanks. Maybe I could invite Rodrigo to comment and say, Rodrigo.
Well, I mean, my opinion comes from this process standpoint of view, how nowadays, like, all these computational workflows are being created. We are actually, like, coming from a very different backgrounds. I'm a Nicaraguan architect, and I kind of like learned old school methods of construction, and being able to like have access to this kind of technology is mind-blowing. And honestly, I think that my particular interest is it's seeing how these the computational developments have been growing and creating one whole chain of actions and elements in which we can integrate not only the designer but also industry, which is very, very important nowadays. And it's we're actually right now in a highly experimental era. We are part of history, as it's been said before. So so being able to craft all of these processes and test them out in different scenarios is really important. And moreover, the difficulty to integrate this and work together with all these different specialties, because when we're talking about 3D printing, it's not only the design, it's the machine, it's the people that are working there, it's all these specialties that are coming all together to do that, you know, and seeing the evolution from our very humble design, the first bridge that we did, and seeing how rapidly this has been evolving. We can really see the projection of where this particular way of producing is going to come up in the future, and obviously it will depend on the technology that you have in hand. It will depend on where you're located. It will depend on if you're able to work on site. So that will define the technology that you will have it there. And actually how you can integrate that all in that in the process. I think it's fascinating that every project that we're seeing is completely different from each other, and it all starts from the methodology that you're working with, the type of printing, the bridge that we designed in the beginning. It wouldn't be able to do that if we would have used layering printing, like what they're using Shajay and Philip. We had to take we took the advantage of using layered printing in order to break away from these shapes, in which this is the philosophy that Enrico has been following through the invention of his machines, and obviously all of these will have a direct impact on the result of the bridge of the design itself. We have for example, other investigations where Alex Dubor, which you know very well, with Edward Cabey, they're leading the 3D printing with clay. This project from OTF that it's been developed for already like 10 years. In fact, I remember that the first project came out of this was Pilos, which was done by my dear friend and also tutored by Enrico. Remember that? Like,
this was student.
Exactly.
I
yes,
only one student.
Yes, and that point you decided to change the strategy to go layer by layer, but working with materiality, working with the idea that you could bring the robot to the site, use the material that you have available for you, convert it, and use it there. So converts the whole idea of the economy of the project itself. You know, it creates a local economy and circular economy as in de facto. I was actually there in the beginning of this project, so it was very interesting to me to see the limitations of the material, and in the end, I think that what we see and what we should take advantage is these highly advanced computational methods, and really take inspiration from what we have available with the nowadays in order to produce.
Thanks, Rodrigo. Let me call upon Shajay to maybe offer some reflections on the other presentations. Shajay.
Yeah, no, I think like it was fascinating to see Enrico's presentation, which I have not seen in its entirety in the way he presented today. Particularly like what struck me was like he started with those two historic bridges, and one of them was like designed by Francois Ennebic, and as we all know, like the Ennebic patents, along with like Corbusier and his Maison Domino diagram, like really helped propagate not only the new technology but also new ways to design with that technology, like all throughout the world. And like to the extent that like when I was studying in India, I had no idea like what is the source of these technologies, but like we were exposed to these diagrams, like, and I think like so in one of the value of like this accelerated experimentation in 3D concrete printing, I believe is like to be able to transmit it through appropriate design techniques, but also design philosophy, like which will allow it to have mainstream impact. And like we also hopefully we can show like through Philip Yuan's like extraordinary work, like over the last decades, like where he's transmitting this information like to the newer generation, like through also DigitalFUTURES. And so we can really hope that like these ancient ways of designing can actually be revived and upgraded and enhanced and they can genuinely form the basis for new experimentation, rather than like trying to reinvent things without looking back at history. And so that's one of the things that like really struck me about Enrico's presentation, and also how things can build rapidly if you stand on the shoulders of giants, right? And that like every technology needs to be paired with like a designerly method of thinking about it and reasoning about it. And so computational platforms, open source computational platforms, definitely is one of the backbones of collaboration, one of the common language of collaboration, let's say. The other is indeed like geometry, right? Like something visual. And even Berok Kushnevitz himself, like kind of talks about geometric reasoning and how can you reason about what shapes are possible with 3D concrete printing. And he again looks at the atlas of shapes which were previously done in masonry construction, and so we are now building on those early ideas, and we now have the tools, we have like the demonstrators, and like, so I think it's an exciting time to be in the profession. And as Philip mentioned, like the metaverse doesn't necessarily need a material basis, but like if we do have these open source tools, and like they're very, very compatible with gaming technologies. So rather than make boxes, why not design with these new primitives? And that's definitely one of our attempts is to transmit this to the new generation of designers who are growing up, like the 3 billion gamers that are growing up today, like expose them to these new things rather than the kind of 20th century maison domino.
Thanks, Shajay. I don't want to keep the session going too long because I know that it's very late for Philip, but there are two questions in the chat. Maybe we can just quickly address those. The first one is for Philip. How accurate are the digital computations versus the physical models load tests?
Yeah, that's a good question. Actually, I'm a professor at the same time. I have an office named ArchiUnion. And also the nomination Archideli last year, we had 3 projects, and I sent to the chat room. And actually we're doing a lot in the real project. Actually, when we're teaching the students, we can test to failure, but if you construct a real building, you should never test to failure. You should prove all your design are accurate. So I think different material, we have different progress. For example, we have the modified plastic printing. Actually, we already implement in the real buildings. The material has very high performance because this kind of composite material have a very stable and very good in control for all the details and joints. But the concrete is a little bit difficult because when we print in concrete, maybe Shajay can also add in some points. The joints between the concrete is the most difficulty. Although we can calculate and design them in the computer modeling, but if we put them together, the different components should meet each other, touching each other, but the joints is really difficult and really dangerous sometimes. If it's not 100% touching, it will be broken because of some mistakes in between them. So we're testing different materials in the design process. That should base on the very long-term improvement. For example, I show in the last project, which is a 3D plastic printing. We put them into the material lab in the city, and every day can represent 1 month. So we're testing for a very long time, for 15 years, if this material should be strong enough for all the details and the load test. So I think everything should be proved not by an individual designer, but should be proved by some regulation and different tests. And after that, we can implement them into the real scenarios. So yes, that's a good question. We have a long way to prove all this kind of new technology into the practice. Thank you.
Thanks, Philip. There's a question for Shajay. I wonder if there was a consideration to reduce or eliminate the need for scaffolding.
Yeah, good question. We definitely did consider it, like to use standardized scaffolding systems like from Perry or others, like so which can easily be reused, and or it also is more precise to adjust the false work needed. It just so happened that, like, because we wanted to demonstrate like the principles of or the congeniality between unreinforced masonry and 3D concrete printing, and like focus on the sustainable digital concreteness of the project. We weren't able to fully pay attention to the scaffolding system, and which is indeed one of the things that in the next version, like whenever that will be, like one of the topics of refinement and innovation is the scaffolding system. Having said that, like the scaffolding was entirely made of like dry jointed waffle system, which hopefully in the next iteration we can refine to either fully eliminate or start using these kind of spider things to hold the blocks in place temporarily. So once the arches are fully engaged, you don't need the scaffolding. It's and so that, yeah, it's definitely a topic that we are looking into to eliminate really like the scaffolding, or use standardized systems from Perry and others, like yeah.
Thanks, Shajay. Do we have time for one quick further question? It says
Yes. Yeah,
yes.
we can take
Do you have some references to 3D printing to seismic zones? Well, that's a big question.
Yeah, I'm not an engineer, so but I can maybe perhaps paraphrase what I've heard Philip Block answer more eloquently about this topic. Like one of the things is about the unreinforced masonry, or generally masonry paradigm, is that you can allow, particularly because it's not rigidly jointed, like there are many during seismic action, like the structure can find alternative stable conditions. And so it's unlike reinforced concrete, where like and rigid fixings, like the structure has flex, like so I don't know if like you see, like in the simulation we were point loading to like to the extent of like 3 or 4 elephants like standing on a single block, and still like the what happens is like the feet get displaced, but the structure is still in equilibrium. So that's one way to think about the masonry paradigm and its suitability to even seismic zones. And the second is like the apparently like in traditional or historic masonry structures, between blocks they use lead pads, and that allows for dissipation of force, like because you want to, in an earthquake, you don't want to resist the earthquake, you want to dissipate the forces. So, and in both the masonry paradigm and like the using of the lead pads, like it follows this principle that you find ways to dissipate the energy rather than resist it through extremely rigid construction. Yeah.
I don't know whether, Enrico, you'd like to add anything to it, because you come from a country which has suffered from earthquakes. Indeed, many of these great historic buildings, I'm thinking about Assisi and so on, which have been destroyed by earthquakes. Would you like to say?
This is a fantastic question, Neil, for me. I mean, a couple of years ago, I was invited to the Minister of Instruction in Italy, and I was very excited to go there. And when I was admitted by the minister, he was intrigued by 3D printing, and he said, "Mr. Dini, would be possible to print a new school in the area flattened by the last earthquake in L'Aquila, in Accumuli, that has been completely flattened. And I said, Minister, I'm honored, but it's we are talking about 3D printing out of concrete, so it's not easy, at least for my system, to propose something that makes sense without reinforcement. But when I came back home, I realized that I was completely wrong, because if you go back in the late 1600s in Sicily, there was a heavy earthquake, and when let's say the was nominated by the vice king of Spain, because Sicily used to be under the Spain kingdom, was nominated an architect to rebuild. The architect couldn't rebuild with other methods rather than building load masonry building structure. So he had to reshape the same material with different shapes. And what he did is so fascinating, because okay, he made the building lower and straight wider, but to avoid the tilting of the facade, he brought the columns ahead, and instead of making the facade straight, he made it turned. So if you Google any church in the Baroque, you will find that the shape were, say, topology optimized for resisting to earthquake, playing simply on the shape factor. So I came back to the minister and say it would be possible to apply 3D printing for into seismic zone if we apply, let's say, topologic optimization to optimize the shape to avoid the tilting of the facade, mimicking the shapes adopted by this man. And this method of building in a seismic construction by load masonry building structure was so new, so novel, that when the tourists of the Grand Tour in the 1700s used to go to see the new rebuilt towns of the Noto Valley rebuilt by this novel method of construction, anti-seismic, they called it bizarre, that is Baroque. So we might say that Baroque is an antelitteram topologic method of construction in anti-seismic zone for load masonry building structures. This is my thing. This is my opinion.
Thanks, Enrico. I was just thinking about that you use the expression dinosaur for Dini, which of course you're not, but I was thinking of Baroque Nevis when you said Baroque at that particular point.
No, we might talk about Baroque 2.0, Baroque in terms of Barocco. The Barocco Siciliano, exactly. Not the Barocco.
Exactly. We're going to wrap up now. We could go on forever, but I know it's very late for Philip Yuan. It's 12:20 in the morning in Shanghai. This has been, I think, a truly historic session. And I want to say one thing is that go back to Enrico's country. I used to work on Alberti, and I translated Alberti from Latin into English. Now, what was important about Alberti is that he wasn't a kind of historical figure. He was a revolutionary in his own way. He was one of the first people to write in the Italian language and to produce this beautiful language now that we have called Italian. He was a revolutionary. And I think it's important to see that we have to see the past and the future in a kind of continuum. There's a lecture that Wolf Prix once gave called In 2 days' time, tomorrow will be yesterday. And in fact, actually, we could even say tomorrow, today will be yesterday. So we are in many ways part of that continuum. And I'm struck by, in a way, we are making history, literally, as we are talking here today. I think it's incredible what we've seen today, absolutely remarkable. And I really hope, Philip, this becomes a book, because it reminds me of a moment in history. Back 2002, I think it was, at the University of Bath, where we had this conference, Digital Tectonics. Mark Burry was there, Cecil Baumann was there, Greg Lynn was there, Mahmoud Lander was there. And it was a particularly historic moment, and and in a way we have a Digital Tectonics 2.0 today in this session. But it struck me also, there was someone in the audience, a student who was just about to graduate from the Architectural Association, who was there that day. His name was Akim Menges, and of course he's gone on to make do great things. I am sure today in our audience out there, there is another potential Akim Menges of the future, and it's a fantastic contribution that everyone has made today for the future. We will be uploading this as a repository in our Digital Futures library to make it available for information, for research material for the students all over the world of the future, and available for free in the spirit of Digital Tectonics, so Digital Futures. So I just want to thank everyone today for this coming together for this session. This has really been a remarkable session, absolutely amazing. And it's thanks to your generosity that we can share this knowledge with everyone else, and that is the heart of what Philip and I have been doing with Digital Futures over the years, to share information for free for everyone all over the world. I will finally say that there is something incredibly interesting, I think, that is happening right now in terms of the word intelligence, because Philip has just launched this journal, the theme of intelligence everywhere in what we're doing, and it's theoretically it's an important sort of issue. Tomorrow we'll be talking about how we're looking at intelligence through AI and neuroscience. This has been fantastic. Thank you, everyone, so much. I want to thank also the team behind this, because none of these things, we saw today that none of these bridges could happen without a team behind this. I want to thank Bavleen for live streaming this, Gustavo for all the team that are giving up their time for free, volunteering to make this material available. It wouldn't happen without you. Thank you so much. Bavleen, do you want to say something about next week's session?
Yes, next week we're going to have another session, tutorial session. We've been doing our tutorials on first and third Saturday of every month. Next week is going to be another session on Grasshopper and linking it to fabrication, which is going to be super interesting. And we hope to see you all there. Thank you.
And we look forward also to seeing Philip's next bridge, in the moment. This is history in the making today. And thank you so much, everybody. We will see you all next week, and also tomorrow if you want to be there. And thank you so much for all our contributors and for the team behind it. Thank you. Thank you.
Ciao a tutti.
Bye.
Ciao Philip.
Thank you.
Ciao.